Ciao and welcome back to the University di Politecnica Ancona. In the previous video we looked at the measurement of shielding effectiveness using a reverberation chamber method, and in this video we're going to move to a more practical measurement of radio wireless propagation channel created with a 5G base station right here. However, before we begin experimenting with the base station, which doesn't actually give us a lot of useful information about the fundamentals of radio channel, it only outputs the specific KPIs associated with the channel, such as throughput, rank, or SNR, or RSRP, for example. But before we do that, we should really understand how the wireless channel propagates inside the reverberation chamber in the first place. And there are two fundamental ways in which we can visualize the wireless channel, which are the time domain and the frequency domain. So in the previous video, where we looked into the shielding effectiveness measurement inside the reverberation chamber, we looked exclusively at the frequency domain, where we were seeing on the x-axis the frequency and on the y-axis the amplitude. Now, today, we're also going to look into the visualization in the time domain, because this is really critical for understanding the multipath propagation, where you see that in time you have different peaks which effectively correspond to the distance of the propagating wave. So we're going to look into this setup first without the base station, because when we actually turn on the base station, it considers all of these time intervals together, so it sums up within a particular period all the propagating waves and modes, and therefore it constructs the throughput, where it can have multiple channels in a multiple input, multiple output MIMO setup, where each channel has a signal or different chunks of signal propagating through it, and then they are all summed up at the base station in this channel sounding kind of setup, which we call, and there we obtain the actual throughput from all of the propagating modes. Now, of course, that is why I said that this metric is not the most fundamental, because we really want to first look at individual channels before we look at the throughput. And this is where the reverberation chamber is really a unique environment where you can play and tune those propagating modes and increase or decrease the reflections by adding absorbing elements into the environment, for example, such that you can tune the K factor, which is the ratio from the first order reflection to the second order reflection, and there you can control the environment, so you can simulate different environments. So let's go back to the chamber and have a look at the wireless channel in the time domain.
So for calibration, we just connect cable end to end.
Okay.
Ah,
Now it's calibrated, so
Now
the
it's
statute
calibrated.
1 is 0 dBm. And now we can reconnect the antenna.
So then we reconnect these dual polarized antennas back, and we have two antennas in this setup facing each other. So we want to see the line of sight in a PDP power delay profile, so that we should see a spike, a tall peak. That's the arrangement. Okay.
So I think that this pulse is a direct pulse.
Nice, probably. If I just stand there,
You decrease
is
the...
it affected? Yeah, you can see. Right, actually. Okay. So we see we can calculate.
I also
the
have
distance
a meter
from
if you
PDP,
want to check.
And yeah, that seems
It should be
correct.
the distance between the two lengths of the antenna. Because we calibrate
With cables, yes,
we calibrate at the connector, in the connector of the antenna.
because we calibrated. Yeah.
Okay.
Okay, so we now enabled.
Now the multipath is very, very low because of the configuration. I think the next step should be to
So that's with the steerer.
point in this way, the antenna, or point it to the steerer to see if there is a direct path and more enhance the multipath.
Okay.
Now if you please stop.
Yes, it's going to zero position.
You can see, before I saw that it was...
Okay.
Because this level is the noise level.
Yeah.
So maybe in some position we have
We don't see
some
much
higher,
multipath.
because we place everything lower than this should be zero.
Yeah.
But is also a come si dice, noise due to the transformer inverse FT. So it's a numerical noise also. I think that if you have something, for example, minus 50, like this or like this, I should be a real peak due to some reflection. Now, I think the second step should be to try to point one antenna toward the steerer and see what happens.
Yeah.
We expect that the direct path should be at a higher distance because it makes some what we expect. I don't know if we really see that.
So now we rotated one of the antennas towards the wall and the steerer rather than directly pointing at another antenna. We see that the PDP changed.
For example, I think that it is the back
This is a
radiation,
Yeah, first.
and the next peak is due to the reflection of the main wall.
This is a main
So
wall.
it's about
Okay.
some peaks that grows and then decreases depending on the steering position.
Okay.
What we didn't see before because
So we now place both antennas away from each other and cross-polarized to reduce the coupling, and we repeat.
so you don't see
Now there's no peak here,
now what should be in
so that's a realistic.
Scenario for, and if we start moving the steer, we can see some peaks growing, and then depending on the
So
steering
we,
position.
I guess when we catch the Snell's law of reflection and the main reflection, that's when we will see a peak, when the steerer catches normal angle reflection.
but it doesn't happen very often.
If I make a single sweep, for example, we try to get some shots. For example,
yes.
in this
like
case we have a multipath effect here.
Okay.
It's just a case at a distance of about 11 meters, some multiple reflection. Then if we make another, for example, depending on the stereo position, we have different.
But they're all very small, I guess, because
because
the aperture of a stereo is quite small. Yeah. So I guess that's what happens when you put a reconfigurable intelligent surface.
For example, here we have some just.
But when it's so small, the effect is also very small. So we are, between 2 and 8.4 gigahertz, right?
Yeah.
Between 2 and 8.4 gigahertz.
2 because it's the lower frequency of the antennas.
Yeah. So I guess in a higher frequency it would be easier to catch, right?
I think that the higher is the frequency, the more effective is the steering action. So you see less peaks, but more uniform distribution.
Okay.
Because depending.
Even less peaks. Okay.
When the steering is moving, you see that each stereo position responds to different, so you don't see nothing as
okay. Sometimes
irrational.
And then you turn average.
If you turn average on, you can see, as before, the backscattering and then the other multiple reflection that decreases with has increased the path loss attenuation.
All right. Yeah.
As I see these graphics.
Okay. So now we repeat with absorber.
So if we repeat with absorber, I think that this peak should be almost the same, and the other should be lower.
So then we are adding some absorber material in the chamber to increase the K factor, and we will repeat that. Oh, careful. Okay. Is 3 pieces enough? I think. So obviously the more absorber material we add, the more it starts to resemble the anechoic chamber, where we don't have any reflection. But this is a way you can tune the amount of reflection in a reverberation chamber. So you can make it slightly less reflective by doing that. That's without averaging, looking already very different.
But unlike the previous scenario, also without average action, we have a more evident decrease.
The slope, yeah, is
because
evident.
the multipath effect of chamber is reduced.
Yeah.
We see a peak before because
peaks, yeah.
okay, some peaks because
you see them coming up, yeah.
There is the direct path.
Because of the
then
yeah.
if we
average, okay, the peak is much
the peak
taller.
is higher because maybe is due to a path that is.
But I guess it's a stereo path, is it or not?
Now they are in NLoS, so there is not a very big direct path.
Okay.
You can see that now this peak is lower than before because the Q is lower.
Okay, Q
and
factor is lower, yeah.
Also the so-called direct path has involves the losses, and
but
the slope is more evident.
I see it's sometimes rising, sometimes going down.
Because now we have averaging, so we
it depends on the stereo position. Yeah.
If we then we can put off if we put off the average reaction within some points, it should be very high.
Very high, yeah. It spikes up. So I guess that's more like a very realistic environment, multipath, where you get random fluctuations because of objects, cars, vehicles, UAVs, anything.
Yeah.
And yeah, that's how you can simulate it. Okay, well, that's pretty cool. And then with the base station measurement, you just do the same type of measurement, but you connect it through a base station and you analyze the radio channel, right?
Yes, when you use a base station real device, we measure for example, the received power directly into the receiving element. So we don't use the VNA.
Okay.
We have to connect the receiving with, for example, SMMP, and then we can see what is so with the Azure off, you can see, for example, now this point is very low.
Yeah.
Then there are some positions very high.
Some position is very high. Yeah.
But with loss, you can see the slope of this.
The slope is still linear. Yeah, decrease.
What not happen without loss, where there are more.
Without, yeah, I see. Without absorbers, you don't see that slope.
No.
Yeah.
Without average, you just see some position higher, one peak.
No, I see.
Because now we are reducing the effect of the reflection of the wall because they are alternated from the sovereign.
Okay. So this position happened to have a very high, so that what probably a reflection from the stereo, isn't it?
We brought in the paper and demonstrated that measured that when we introduce losses, in the best cases we better the configuration. So losses makes a better configuration expected without loss.
Okay.
But the worst configuration is worse. So
the worst is worse, the best is best.
Yeah.
Better.
Because if you have, for example, a 2-3 reflection, all the other component of the field is a noise.
Yeah.
But if you have just a scattered link between the transmitter and receiver, all the reflections are signal.
Yeah.
So we see also at different frequency with that losses betters the best case, and the worst is the worst case.
Interesting. Well, that's quite cool. I'm just interested to see at what position is this. Is it gonna go away? No. So, okay. Oh, that a bit makes sense, doesn't it? So, see the antenna actually looking directly at one of the plates, and it probably bounces off these walls back into antenna number 1. And that makes it a very direct path. Okay.
So by doing this type of measurement with a base station and a mobile terminal inside the reverberation chamber, we can simulate various types of complex propagation environments, such as high-speed trains which experience high Doppler shift in frequency due to fast movement of a user terminal relatively to the base station, or tunnels where we experience a lot of multipath and reflections, and even we can simulate the effect of water pouring down due to rain on the especially millimeter wave propagating signal is significantly affecting that. So there's very different and interesting options that you could do in a reverberation chamber with respect to over-the-air testing for mobile terminal handsets. So I think this is about as much as I could talk about in this video. Please like and subscribe the channel and let me know your thoughts in the comments. And what else would you like to learn about with respect to reverberation chamber testing? It would be very interesting for me to know as well and get some feedback. So by all means, let me know, and I'll see you in the next video shortly.